All right. We are now recording. Let's start from the current slide. I don't know why it won't start from the current slide. I'll try it again. There we go. Any questions on anything we've done so far? All right. We're on page 40. This is chapter 2, first order differential equations, 2.1 solution curves without a solution. Okay, we're not necessarily finding a solution. Some of these may not even have solutions, but these are ways you can approach a problem like that and come up with good estimates. Okay. Now, we were talking, we were just about to get to example 3, which is, big old word, an autonomous differential equation. And here's an example of one of those. Let me get my pen set up. Okay. dP dt, time rate of change of something, pressure, population, anything, I guess, is equal to P times A minus B times P. Okay? Now, just off the bat, you'll get sick and tired of hearing me ask these questions, but just to get an idea, what kind of differential equation is this? Second? I couldn't hear. First order, absolutely, and that's what this chapter is about, so that was a real good answer. Okay, and let's see, this is, yeah, Rod, got it. All right, so it's first order. Two other classifications. Ordinary, good deal, and okay, is it linear? Yes, because it has a p squared. If you multiply the p through, you would have PA or AP minus BP squared, which knocks it out of being linear. So it's not a linear one, it's a nonlinear, but yeah, perfect. Okay, now, in this one, A and B are any positive constants, and it has a normal form, what they call normal form, of dP dt is equal to some function of P. Which is, if you go back, the reason they bring that up is page 39, when we first introduced autonomous differential equations, we said that's the form they would be in. Okay? The other way to express that is if you were to move all the p's to the other side, dP dt minus f of p, or whatever they called it, f of p, then that's equal to 0. So that's what classifies it as an autonomous differential equation. Now, the ones that wouldn't be was one that would then have an additional term, q of x, or g of x, or anything of x that has no p's associated with it. So this is autonomous because all the terms contain a p, okay? None of the terms don't contain a p. In other words, if you wrote up all with the p's on one side, then you have a 0 on the other side, which we also call sometimes homogeneous, but this is autonomous, okay? It's Taylor, right? Or Monica? Yeah. Monica? Okay. Okay. Now, so what is your independent variable then in this differential equation? Second? It's the t, yeah, the t part of dt, yeah. So the dependent variable would be p, and the a and b's are constants. Got it, okay? So this is an autonomous equation. Now, what if And to lead from something that was up above, if you talk about the critical points, a constant solution, y is equal to c, is called an equilibrium solution, okay, for an autonomous differential equation. Well, what if that c were 0, okay, where the f of p, in other words, the right-hand side is equal to 0. What would make that true? If the right-hand side were 0, p times a minus bp equals 0, what two conditions would you have for p? Either, think of that as being a linear, not linear, a quadratic equation in p. And we want the two possibilities where that would equal to 0. What values of p would give that to you? Okay, p is equal to 0, certainly would. And, or, okay, well, let's break it down. The other half of this would be a minus bp equals 0. Because this is zero product principle. Two factors multiply to make 0. One of those two has to be 0. Either p is equal to 0 or the other one's equal to 0, right? How we used to solve linear quadratic equation. I keep saying linear. Okay? So what's the result of this one? What would you do? To solve that for p. Here, this is already solved for p. Second? Don't think so. Then you would have a is equal to 0 in the second. Second? Okay. I'll buy a over b. Okay. All right. Because if you add BP to both sides, that's British Petroleum, or it used to be anyway, that will wipe this out, and you have, I'm going to swap sides, BP is equal to A, and then divide both sides by B. So yeah, P equal A over B. So there's two possible solutions or situations in which your this function, or this would have an answer of 0, okay? So these are your critical points, okay? By putting the critical points on a vertical line, that seems a bit bizarre, but this is going to be your p-axis, okay? But that makes sense, doesn't it? Your independent variable is on the horizontal axis, the dependent variable on the vertical. You told me p was your dependent variable, so this is on the vertical axis, and we want the places where that p is equal to 0. In other words, where it's on the axis, okay? Well, not on the axis. The values for which that's 0, okay? So that's going to be at p is equal to 0, we'll put down here, and p is equal to, this is the p-axis, a over b, okay? This is where it's 0. Now, of course, a could be negative and b positive, so that would put it down here, or b could be negative and a positive, and that would put it down here, or they both could be negative and that would put it up here. It doesn't matter really where it is, but those are your two places where this is going to be, the function is going to be constant 0, okay? The function itself is, okay? At those values. So what we usually consider there is then, for any value of t, by the way. So that's going to be, if you remember how it looked before, this is basically going to be a line like this, and this is going to be a line like that, okay? So now what we do is consider values outside of these two and between the two. Now, if there are 3 or 4 of them, you keep putting in one on the outside, one in between every one, and one on the outside here. And those would be then the points that you would consider, okay? And the arrows, and you don't see the arrows here, Or at least I see them. Okay, got them. I thought they were just points. What you do here is figure out what's happening to the function. It's either going toward or away from these lines. It's either increasing or decreasing. It can't change, because if it changed, you'd have another 0, right? So the example they give here is this is coming toward P over A, the one in between is going toward P over A, and the one below is going away from 0, okay? So this one must be going away from 0. So already now you have some ideas of what this function looks like, okay? And they're not doing anything above, but looking at it, this would be probably approaching like this, okay? This one's probably going something like this, because it's going away from 0, but it's going to be constant there. And this one's probably doing something like that, going away from 0. That is, in general, how the function is operating. Okay? Find your zeros, and then evaluate the function somewhere above, between, and below those various zeros. See what the sign or the order of that function is, and that then will tell you which way it's going. By the way, that's given by the dp/dt. Okay? So let's see if we can do, and this is something they call and I mean, I'm having trouble with this because they're just sort of making things up here. Suppose this, suppose that, this kind of stuff. So this is called a one-dimensional phase portrait. What a strange name. Without my lines in there, you're just looking at that one-dimensional p-axis. You got the two zeros, and then the places where p is equal to 0. No, not p is equal to 0. The function's equal to 0. And then you also figure out which direction it's heading in between. Okay? Now, without solving an autonomous differential equation, which we're not even going to try to solve that, we can usually say a great deal about the solution curves. Okay? So, say in between the two functions, and why they changed to a different one, you can tell the general direction they're heading. You may not know exactly where it crosses or anything else, but you know generally where it's headed. Okay? And so they show another that's not the same one here. Y'all don't have your books, so let me draw that one. This is on page 40. Okay? They show another region. Okay, and this time they're in X and Y, X-axis, Y-axis. They know this point is on the function. That could be your initial value problem, X0, Y0. Without being able to solve it, if you know it's a situation like this one up here, then you know the function's going downhill there, okay, unlike the one that we showed there. So more than likely, it's going to be approaching a horizontal asymptote somewhere here. And more than likely, this one will probably be approaching somewhere up there, another horizontal asymptote, unless it was one like this, and then it just be heading up without any limit on it. Okay? Now, your constants, and this time they don't have to be 0, where your y's are some constant, which we call the equilibrium solution. If that was somewhere enclosed in here, you could have a y is equal to C1 down here, y is equal to C2 up here. That means that's going to be constant at those values. So then you know your function has to smooth out and approach those values in the long run. Okay. And again, this is sort of esoteric. It's just giving you ideas about functions that you may not be able to actually solve. Okay? Okay. Now let's just go on to example 4, which is a revisit of example 3, which we did last time, or at least did parts of last time. Okay? Example 3. Well, no, yeah. Wait. No. Well, that's what we just did. No, that's the one we were just working on. Why did I erase it? The 3 intervals there, sorry, I erased that. The 3 intervals, let me go on and draw them again. Here's your p-axis. Here's your t-axis. Okay. And t is equal to 0 was one of those. You know, basically I've already done this, but not quite completely. Okay, this is your one of your values you know already, and here's the other. This is where this is 0, and this is the a over b. Okay. You know you have basically a horizontal asymptote there. Okay. What this is breaking the space into an R1 down here, where we know, remember our little arrow said we're going downhill, so it's doing something like that. If all you needed to know was some value, and I don't know why they call them all P0s. I would call them different things. In R1, that would be your the shape of the curve there. If it had to pass through this, which they also call a P0, I'm going to call it a P, well, I'm going to call this a P1, and this a P2, because they call this region R2. Okay? And if you know it crosses there, then it's got to do there, because you knew this directional derivative. In other words, your derivative was positive in this region. Then, and up here, remember, we said it was decreasing, so it could be coming from anywhere up there. But if you knew it crossed there, we'll call this P3, and that will be for region 3. Now, they call them all P0s, which I guess is okay, but it just seems a little confusing. So, the reason they did that, they're 3 completely different regions. In this region, your initial condition could be that. In that region, it could be there. And in that region, it could be that. So 3 completely different. For this to be a function, it can't be all 3, right? You have to choose where you are. Where you are, Waldo, okay? Which part are you in? If that's your initial condition, you're down here. If that's your initial condition, you're up there. And if that's your initial condition, you're there, okay? So probably the zeros make some sense, but all right. And t's are good from positive to negative infinity, so neither one of these are approaching vertical asymptotes. They're just increasing forever. Okay. And again, this is sort of out there. There's nothing. It just gives you an idea of where to start. If they just gave you a differential equation with some values in them, that might make more sense and make it, seem a little more reasonable. Example 5 does that. So I think what I'll do for example 5 is, I think I did too much. No. Okay. I could have just done that. Sorry about that. All right. Example 5, we'll use the graph. Autonomous differential equation, here's one. dy dx, oops, let me get my, oh yeah, because I turned it off. Sorry about that. dy dx, first order again, ordinary, those aren't partials, is equal to y minus 1 squared. Okay? Now, That's the first derivative. Okay, I said it was ordinary, first order. What's the last part? Last classification. Nonlinear again, because the y is squared there. Okay, very good. Now, what are its critical points? In other words, where is the first derivative equal to 0? Same thing from back in Cal 1. Where is the first derivative equal to 0? There's the first derivative. Where is it equal to 0? At. Second. Where is this thing equal to 0? What value for y? 1. Yes, y equal 1. There is your critical point. And this is your y-axis. This is your x-axis. So since that's the only thing we're going to have on our graph here, how many spaces, blocks do you want to represent 1? 3, 4? Just so it won't be, 2. Okay, we'll make it 2. So here will be 1, 2, 3, -1, -2, -3. Only reason, that's your critical point. That's where your first derivative is 0 everywhere. Every value for x, your first derivative is 0 when y is equal to 1. Everywhere. That's a horizontal line. Okay? And here's Lauren. Okay. All right. Now, second bit of information, when you're less than 1, y is less than 1 or greater than 1, what is your direction of your derivative? Pick a y greater than 1. It's positive. Greater than 1, this is going to be going uphill. How about less than 1? Negative, exactly. Because you're going, no, wait, what are you telling me? What's your derivative? Derivative is? Say again? Positive, because you're squaring it, okay? So these are positive in both situations, okay? Yeah, the y may be negative, but the derivative is positive, because whatever is in that parenthesis, you're squaring it. And the only place where it's 0 is at y is equal to 1, okay? So, there we know something about this differential equation. Even if we don't know how to solve it, we know something about it, okay? Now, and that's good for all x's everywhere, negative infinity to positive infinity. Okay, now what if you knew for an initial condition that the y of 0 is equal to y1, let me write it, y at 0 is equal to y sub 0, okay? But that value is greater than 1. No, I'm sorry. No, less than 1. And that value is less than 1. You know that, okay? Now, your x, of course, is 0, so you're going to be somewhere on the y-axis here. And your y is y0, but it's something less than 1. You get to pick any value less than 1. Pick a value less than 1. 0, okay? That's a perfectly fine one, less than 1. And x is 0, so you know this point right here is on the graph. Which way is it heading? Up, okay? So the curve could look something like that, okay? It can't, it's got to be approaching a slope of 0 the closer it gets to y is equal to 1. So it's some sort of a function that looks like that. You know it's got a value. If you know its initial condition is this, if that's less than 1, it's down there, okay? And this is why they use the p-zeros on all of them. But what if, on the other hand, you knew that I lost it here. Okay. For the initial condition, say that y0 is equal to 2. Let's do that in a different color. What color you want it? Red. Okay. So what if we knew, on the other hand, that y at 0 was equal to 2? And that, of course, is greater than 1. So what would be your... First, you know that y is equal to 0. When x is 0, y is 2, so you're right there. And which way is it heading there? Uphill again. So now we know you have to be, that would be it. Both of those can't be true. Y at 0 can't be two different values. It's either something, if it's equal to 1, it's a constant function. It's not ever going to change, okay? If it's less than 1, it's going to be going like that. If it's greater than 1, it's going like that. And you know the intersection. You don't know the shape of it, okay? This could be a very slowly increasing function, or it could be shooting up there. And same thing here. You don't know what, but you know it has to pass through there, has to be increasing all values of x. When y is greater than 1 or y is less than 1, you know those things have to be true. If y is equal to 1, it's going to be 0 everywhere. All right. Now that doesn't tell you a lot, but it tells you a little something. Okay? Now, more than we know, because we don't know how to solve that differential equation yet anyway. Okay? So let's erase this and go to another. Here's another one. Now, y of x, let me go back to my dark color, back to black. Okay? This is on page 42. Okay, example, it's under example 5. We just did example 5. Now we're doing the one underneath that, which may be part of that. I don't know. I don't think so. Okay. I think I already chose. No, I did. Okay. Y of x is equal to 1 minus 1 over x plus c. Now you can sort of easily imagine that's a one-parameter family of solutions of which differential equation? I guess the one we just did, so this is still part of example 5. Let's just say that's our solution, okay? That's our differential equation, okay? And they say see problem 4 in exercise 2.2, which is quite a ways away, okay? A given initial condition determines the value of C. For example, for an initial condition, y of 0 is equal to negative 1. Equal to negative 1. Okay. Now this is that same differential equation we just did, so I should have left it up there, but I didn't. And we know that's less than 1, okay? So let's go back 1, 2, 3, negative 1, negative 2, negative 3, okay? Now we're down here. Y of 0 is, and this is your x-axis, this is your y-axis, and this was your critical value. You know it's going up here and up here, okay? And here we have y of 0 is equal to negative 1, okay? So you're somewhere down there, okay? Now, knowing that, we can solve for C. So let's plug in 0 for x. Y of 0 is equal to 1 minus 1 over what? X is equal to 0. C. That's yes in Spanish, okay? Now, solve for C. And we know this is also equal to -1, okay? So sort of get this out of the picture. Solve that for C. What would you do? How would you approach that? There's several ways. What would be there's your equation you want to solve for C. Help me, folks. There's several ways you could approach it. Second? You may have said right, I just don't hear well. I hear a little noise when I see mouths moving, but I can't make out what you're saying. Solve for C. There's several approaches. Say again? Okay. Okay, it's 1 minus 1 over C is equal to -1. Which one? The first one? This one? Okay. Yeah, subtract 1 from both sides. Good choice. Okay, that throws that away, and you have a -1 over C is equal to -2. Good. Now what? Multiply what? C on both sides. That would be a good move. So we'll multiply that by C and that by C. Okay? That'll wipe out the C's here, and now you have a -1 is equal to -2C. Now what? Net divided by -2. Okay, and what does that give us? C is equal to +1/2. Yuck, I can't get my equal sign right. 1/2. Okay, that's really ugly down there, but it's 1/2. So now we got C is equal to 1/2, which is what they did. Okay, so now we know our solution, y of x, for any x, is equal to 1 plus or minus 1 over x plus 1/2. It's probably not the nicest way to leave the problem, but you certainly can. That's your solution from your... So we need to figure out where this is, okay? Now, you can either start plugging in values. We already have when x equals 0, you have, this should be 1 minus 1 over 1/2. 1 over 1/2 is 2. 1 minus 2 is -1. So yeah, that point is on there. Good. That makes me feel warm and fuzzy inside. Okay. You can choose any other x that you might want to choose. And since I labeled the y-axis, let me label the x-axis. 1, 2, 3, -1, -2, and -3. I think I'll get rid of some of this writing so it won't be as, we've already used the stuff. Whoops. Okay. I'll get rid of that too. Okay. And maybe this. I'll leave the C is equal to +1/2. Okay. I don't think the rest of it's in the way, but I'll get rid of it anyway. Okay. I'll leave that. Okay. So there we have one point. Pick another point. We did 0. About -1/2. -1. Okay, you could do 1. You're a hard worker, I can tell. I'm lazy like you. I mean, I'm lazy too. Okay, I want to go with 1/2. X equal 1/2. What does that give you? 0. Okay. You could do the other, but this one's even easier to do. Give me another one. obviously here x cannot be something. What can it not be? It can't be negative 1/2. So what does that make that value? Yeah, no, it makes it a vertical asymptote. It doesn't have a value there. So x equals, I'm going to make that vertical asymptote red, meaning you can't go there. So negative 1/2, here you have a vertical asymptote. Okay? And basically, without much further ado, I can go on and draw in this side. Okay, I'll go back to black. It has to go through there and there. So let's just make this go like this and like that. That may not be exact, but it's going to be pretty close. Okay? So if I choose another x, what might you choose? We know where basically everything over there is. How about x is this way? Give me something. X equals, give me an x. I feel like a cheerleader, right? Give me an x. Negative 1. Okay, again, he's a hard worker. Can you give me one a little bit easier to deal with?
3/2.
Negative 3/2. Okay? How about negative 3/2? Because if you x equals negative 3/2, what will that become? In the number. A negative 1, and that would be 2. Okay, that would be 2. So at negative 3/2, which would be right here, we're going to be at 2. And there's 2 up here. And guess what? I can go on and give you a pretty good idea where this function is going. Going like this. Got to. Vertical asymptote that way, horizontal asymptote this way, it's got to be curved like that. So there is your solution with of the one parameter system. Once you know your parameter C is 1/2. That's how it looks. And there are 2 parts to this. There are any of the values x is from, so we can't say anymore x is good everywhere. It's not. It's not good at negative 1/2. Anything to the left of negative 1/2, there's your function. It's got to be up there. Okay? Anything to the right of negative 1/2, you're over there. Okay? And if this is your initial condition, you can't be over here. Ever. This is the curve you're always on. Okay? That's your initial condition, which that's what was given to us. There's where you are. Can't be over here because you'll never be at, y will never be negative 1/2. Does that kind of make sense? Okay. Now, let's do the second case, and that's the one, and I think we did these before. Are these the same ones they mentioned before? No. Yeah. It's hard to, I don't see it. Okay. Second case, what if our initial condition was y of, where is it? There it is. Y of 0 is equal to 2. Okay, let's do this in a different color. Now, let's not do red because I use that for my asymptote. So what color you want it now? Blue. Baby or dark? Dark. Okay, I like that too. Okay. So, let's say that y of 0, initial condition, is equal to 2, which means you're no longer down here. You're up here. Y of 0 is equal to 2, and of course that is greater than 1, which is your critical value, so you're somewhere up there. Okay? So what's the next thing we're going to have to do? If this is your equation, and you know the y of 0 is 2, what you got to solve for? C, okay? That's yes again, okay? So your y now of 0, and we know that's equal to 1 minus 1 over No, x equals 0. C, same as before. I'm sorry I erased it before. And that this thing this time is equal to 2, not negative 1. Okay? So what do we do to solve for C? Okay? Okay, throw it out. Okay, no. Subtract 1 from both sides. Okay? And that gives you negative 1 over C is equal to 1 by C. Okay? And that's going to give us C is equal to, I'll flip sides. Second? Negative 1. Okay? So now out of that family of curves, the one we use is this one. Y of x is equal to 1 minus 1 over x minus 1. Okay? Now what can you see looking at that one? What can x never be? 1. Okay, so we put our, go back and do, this is why we reserve red. In this case, there's your vertical asymptote. Okay? We're only dealing with this part this time. Okay? Is this too confusing having them both on the same graph? If so, I can erase the old one. You all right? Okay. Y'all are good. Okay. Okay. Now, and we also know that that point is there. We also know here's your horizontal asymptote. You know what? I don't need to do another value. I know this one's going to be right up here and going like that. There's the part of the graph we're on. The initial condition is on there. That's where we are. We can't be on the other part. Let's just, for completeness, give pick another value, something to the right of 1. 2. Okay. And if you use 2, what does this tell you y of 2 would be? 1 minus 1, which is 0. So y at 2 is going to be 0. So here's where this half lives. Whoops. It lives somewhere down there. Except that's not part of our problem. This is our part, because that's where our initial value is. You can't go there. You can't have an x value of 1 or greater. Not going to happen. You're going to be restricted here. So now your I is restricted to an interval, anything from negative infinity to 1. That's the only interval you can have. You can't include 1, but you can get close to it. Okay? Does that make sense? Again, it doesn't solve the equation for you, but it tells you basically about where you got to be. That's your approximate solution curve there. Okay. Does that make sense? Okay. Because we aren't solving those yet. Maybe later we will, but this is just to give us an idea. Okay. Now, another way you can talk about these things now these are autonomous differential equations, those things you can do this with. You can talk about attractors and repellers, okay? I don't know if this is anything particularly valuable to you, but you know, let me introduce the term. Suppose that y of x is a non-constant solution of an autonomous differential equation, not the one we had before, but the generic one. And C is a critical point in that differential equation. There are 3 basic types of behavior y of x can exhibit near C. Okay? C, remember, is your critical value. Okay? And the C here was 1. Okay? Okay? all solutions of y of x of 1 that start from an initial point x0, y0, wherever that happens to be, sufficiently near x exhibit asymptotic behavior in the limit as x approaches infinity. Where is the y going? Okay? So, as x approaches infinity, up here, it's going away from C. So we say C was a repeller. I mean, it can't even get closer. This one up here is going away from C. This one's going towards C as x approaches infinity. So that's an attractor down there. Whichever C you had, I mean, whichever, C you choose. Wait, this aggravates me. They use C to be the critical value, but they also use C to be the constant. Those are different C's, okay? Completely different C's. Just irritates me they use the same one. But the critical value C, that's what you're either attracted or repelled from, okay? As you're going to negative infinity, both of these functions are attracted to that critical value. If you're going to positive infinity, they're attracted to it. If you're going toward the vertical asymptote, of course, they're repelled from it. Okay? So, the critical point C is said to be asymptotically stable. In the long run, on the right-hand side, those are going to C. Left-hand side, those are going to C. Asymptotically stable, moving toward that. Using the physical analogy, a solution that starts near C, like a charged particle over time, is drawn to a particle of opposite charge, so that C is referred to as an attractor. Okay? But when both arrows heads, okay, I think I'm going to have to erase this one because we need to draw a new one here. Okay. Remember back when we did our, I call it tangent mapping. I don't know if that's what they called it. What do they call it? Slope field, direction fields. Did the direction field. It shows which way, how much the tangent was heading. Okay? We found that, say, I'll try to get the same color code they did. Okay? At y is equal to 1, and this almost looks like the same thing we had before, we had horizontal tangent, and all the y's were facing in that direction. Okay? All the slopes were 0 here, but going that way. Okay? Okay. Now, if we had done our direction fields elsewhere, and we found that these were all pointing upward, I'm just going to stop inside there, but these were all pointing downward. You know, we did this early on, okay? All our direction fields were pointing downward. This is obviously a repeller, okay? That would be your direction field for an autonomous differential equation, okay? Now, what if we had another one that was more like this? Let me change the graphic here. And we have your critical values at y is equal to 3. Okay, this time, critical points. They're doing everything in blue, so I guess I'll stay with blue. Okay. You have a critical point. I'm going to use y is equal to 3 right here. So here's your y is equal to 3. There's your critical point. So here everything is going in this direction, not changing, constant. Okay. But you have another one down here at y is equal to 0. Okay. Now, you have to figure out what's going on here. If your direction field is like this up here, that's attractive from the above side, okay, is attractive from the below side, okay, meaning everywhere down here, okay. Remember our little arrows? This would be the arrow down, this would be the arrow up, and in this case we had an arrow down. This is going back to the previous one. So that means down here all your slopes are away. So it's repulsive, repellent I think is the better word for it, from your x equals 0. Y is equal to 0. Okay? So that means whatever curve you happen to choose is, and they do these in red, so let me change these to red. Just trying to do like the book. These could be your curves up here. The curves in here, I think they chose to be purple. Okay, these would be curves like this. They are repulsive from the y is equal to 0, repellent, and attracted toward the y is equal to 3. Down here, I think they did these in green, so I'll try to match them up. And these are repellent from 0. Whatever they're doing, you have to follow the direction field to see what they're doing, but they're going away. Okay? Now, I'm trying to find what they're referring to here, and I can't see it. A critical point exhibited in 2.1.9. Okay, that's the one I've already erased. Okay, remember that last one before this one. Okay, the intermediate one where we had c is equal to 1 here. It was going this way, repelling that way, but attracting this way. That's called a semi-stable, okay, critical value. It's stable coming from the downside, but it's attractive from the downside, not repelling from the upside. So what's unstable? Oh, I see. Goodness gracious. I was jumping ahead on my figures. Since the wording was over here, I thought this. Let's go back to, in fact, let's just leave that alone and go back here, okay? And these are four situations here. Okay. Here's my, in this case it's y-axis. Here's a y-axis, there's a y-axis, here's a y-axis. Okay? In every case, we're going to put our critical value, we'll put this in blue, C to be here, and here, and here, and here. In every case, the critical value is in the same place. But what gets important here is your direction fields. Okay? In the first case, up, down from below, up from, down from above, up from below. This is called your stable states. They're attractor in both directions, so that's a stable, asymptotically stable. That's what it's talking about. In the second case, going in the opposite directions there, that is repelling in both directions. That's an unstable okay, case. Okay? And in the next two, we have what they call semi-stable. This would be attractive from here, repellent from there. Here we would have repellent from here, attractive from there. Okay? Those are your semi-stable states. That's with one critical value. Okay? Now, the one we did here, stable up here, unstable down here. Both of these are repellent down here, both attractive there, stable there, unstable there. Asymptotically stable anyway. Okay. Now, here's another statement. This is called the translation property. And again, they're just sort of pulling these things out of the air. I'm so much looking forward to the next section when we actually start solving some differential equations. This to me is just, it grates on me. Okay? It's called the translation property. But it's sort of important stuff, so we need to know it. So I think I'm going to go back to my other slide, erase this, I'll write it on here. Okay. Excuse me. Sorry. All right. They say you may recall from pre-calculus mathematics that the graph of an equation y is equal to f of x minus k. What did we say that was doing to the function y is equal to f of k? What has it done to that function? Anyone recall? Okay. When either a constant is added or subtracted to either the function, which is y, or to the x, which is the x, that creates a translation, right? So if it was y is equal to f of x plus c, that would be moving up c, unless c was negative, it would be going down. The function would look the same, it would just be going either up or down. When you add or subtract from the x, however, now let's say k is a positive constant, what kind of translation would that be? First, there's a word, and it's multiple choice. Horizontal or vertical? Say again? Say again?
If it was positive?
If k is positive, yeah. It's going to be horizontal because it's changing the x. If you're changing the f, that's the y, that's vertical. Changing the x, that's horizontal. Okay? So you got the first multiple choice right. It's horizontal. Second multiple choice is right or left. Okay. This one's going right. Okay? And this is the thing about the x's. They always go in the opposite direction of the sign. Okay? The y's, if this were a plus k, that's going up. Minus k is going down. With the x's, minus k is going to the right, a plus k would be going to the left, if k is positive. Okay? So that's a translation, a horizontal translation. Okay? Now, if you recall, let's see if I can. Okay? Let's use this one. Let's again go back and call this the way they call it before, R1, R2, and R3. These are the regions there, below, between, and above your critical values. Okay? Now, and I think we're using the same one. I'm actually on the right one here, surprisingly. And those that I've drawn here, what the difference is between this one, this one, this one, this one. If I had a parallel, which I should have, is that would be a horizontal translation. Going this way, it'd be x minus bigger case. Going this way, x plus bigger case. Same thing here. Those are horizontal translations. Those are horizontal translations. Okay? Now, so here's the statement. This is called the translation property. I kind of want to write it on this slide. I just don't have a lot of room to write it. Let's see if I can fit it in at the bottom. And they wrote it in red, so I'll write it in red. I'm being very follow the leader today. Okay? If y of x, if you can read my ugly writing, is a solution, okay, of an autonomous differential equation dE, I'm not going to call it ADE because we don't use it that much, dy dx is equal to some f of what? For it to be autonomous. What variable? Multiple choice again, x or y, or both. Not neither, okay? For it to be autonomous, what must that function be a function of? Y, why not? Okay, can't be a function of x, that wouldn't be autonomous. Why? Because if you put all the y's on one side, you have a 0 on the other side. Okay, that's our autonomous differential equation. Then, y1 of x is equal to y of some x minus k, where k is a constant. Woo. I mean, not right there. K is a constant. Okay. Then there's also a solution. Okay. So if y of x is a solution, and it's an autonomous differential equation like this, then pick any constant k, y of x minus k will also be a solution. So in other words, just like I drew here, if this is a solution, and this is, that is, all the ones that are parallel, you might say, curved the same, everything the same, but just translated horizontally, they're also solutions. Which one you choose? What is your C1? Okay, not C. The C is the critical value. C1, what is the integration constant, you might say, for that function? Okay? Now, the example they give, I think I'll go to black here. Okay? If y of x is equal to e to x for any value x, positive infinity to negative infinity, is the solution for it IVP, intermediate value problem, dy dx is equal to y. And you know that's true. E to that works every time. Take derivative of it, you still got the same function. Okay? You know that's going to be true. When, especially when y of 0 is equal to 1. Okay? Then that will be your one and only solution. Okay? Well, what would happen to if, let's see, so another solution, not of the same differential equation, but a different one. I mean, same differential equation, but with a different initial condition. Y is equal to e to the x minus 5, I think is what they use here. I can't find it. Yeah, x minus 5. will also be a solution, but that would just have a different initial condition. So the family of solutions would be any translatable, horizontally translatable function. Okay? Now, blah, blah, blah. Homework exercises in 2.1. I've assigned some of these before. I would say do either 1 or 3 or both. And the answer to the odd number problems are back in the back of the book. Okay? Then do any of the odds 5 through 11. Do 13 and do 15. 15 is talking about isoclines, which you would use on, say, topographic maps showing areas of equal elevation. Okay? Then following that up, and these you don't have to do, but number 17 talks about a null cline, which well, I don't see where they really define it. They introduce it, but they don't define it. Okay, that was all 2.1.1. What we just finished, 2.1.2, now do problems 19, any of the odds 21 to 27, do 29, and then you can look at, but you don't have to do the rest of those. Now, a few things are talked about there. A critical point, an autonomous first-order differential equation said to be isolated. I kind of hate it when they introduce new terms in the problems, okay? If it's important, put it in the section. Don't put it in the problems. So I'm just pointing it out to you. Not that you will probably ever use it, okay? And then they give some population models some mathematical models, population model, terminal velocity, chemical reactions, some of the things like we did at the end of chapter 1 for autonomous differential equations. So finally, we get to 2.2, which frankly I wish would be where we had started almost. I mean, maybe some about the nomenclature, but chapter 2, all right. I think I need the next slide, and I'll delete that too. Okay. We're finally going to get around to solving some differential equation. About time, right? Okay. Let's consider a first-order differential equation, dy dx is equal to f of xy. Would that be an autonomous differential equation? Why not? It has an x in that function. To be autonomous, it would have to strictly a function of y. Okay? So this is one that is x and y. So a lot of the stuff we just said really won't pertain here. Okay? Now, so we talked about autonomous when that depended on y alone. Now we're going to focus on those in which this really is a function of x alone. No y dependence on the right-hand side. Okay? None at all. This is going to be our equation 1 for a while now. Okay? Now, here's what they say. That equation, dy dx is equal to g of x. Guess what? You don't need anything special. In fact, you probably did this a little bit, but may not have realized you were solving a differential equation. And this is not the verbiage that mathematicians like to hear, but it's kind of like you multiply both sides of the equation by dx. And what they prefer to hear is write this equation in differential form, which would be dy is equal to what? G of x dx. And guess what? Integrate both sides. Okay? So that is solvable by integration. Just split it up, This will give you y minus y, no, or just make sure you can say a y. Assume all the constants are over here. And then if that's an integrable function, integrate it. Okay? If it's not integrable, do numerical integration, do whatever it takes to do that. That will give you values for y. Of course, if you have initial conditions, then you can specify, because this will have, anytime you do an indefinite integration, what do you get? Indefinite integral? Definite integral would have limits on it. Indefinite integral, what do you have? Plus c, you always have constant. Maybe more than one constant, but those are your constants of integration. Okay? So let's see if we can do an example of that. Here's one. I think we can do it without erasing. Okay? dy dx is equal to one plus e to the 2x. Okay? Can you integrate that? I mean, can you solve that differential equation? How would you do it? Right? Yeah, multiply by dx. So mathematicians don't like to say it that way because that's an operator. You don't multiply by bar, but write it in differential form and say 1 plus e to the 2x dx. Okay? And then integrate both sides, and this gives you y. Why not? Okay? Over here, what would you get? X plus e to the 2x 2. Okay? Plus c. Plus c. You have to have a plus c in there, right? Because this is a first order differential equation, you got to have at least one integration constant. Okay? Now, how do you check this? Take the derivative of it. That gives you 1. This gives you 1/2 e to the 2x times 2. 2 cancel the 1/2. Sure enough, e to the 2x. Okay. Take the derivative of that. Because, okay. So, we've just solved the differential equation just by doing integration. You could have done that back in Cal 2, right? Okay. And you may have. Don't know. Okay. Now, that's pretty easy. They actually wrote it this way, and it's fine. X plus 1/2 e to the 2x plus c. Now, time out here. Have y'all ever worked with WebAssign or some of those other packages? Did you enjoy that process? No. Okay. I really think they do have good tutorial help and things like that, but guess what? If this had been the problem and you had written the answer that way, and their algorithm said it was this way, they said wrong answer, it's perfectly correct answer, okay? So that's what irritates me about them. They only recognize a single answer, especially in calculus and differential equations. You can express answers in so many different ways, okay? So that's why if you wanted me to get them for the tutorial help, I'll certainly see if I can do that, but for anything else, I find that pain in the neck. Okay, never mind. I should have said that. Okay. Now, that's, though, just another special case. Remember, if this was a f of y, that would be an autonomous differential equation. Okay? That's one case. If it's strictly a function of x, solved by integration, that's another special case. But the most generic form would be this form, where the function on the right-hand side is a function of x and y. Okay? Now, we're going to be dealing with those for just about the rest of the time. You'll need to know how to do these. If it's a function of x alone, integrate, okay? Function of y alone, go back and do all autonomous type stuff. But if it's a function of both, we're going to look first at a special case of f of xy, okay? And that's what we're going to hit first. That's the title of this section, though we had to get that other stuff said. What if your dy dx is equal to your f of xy, that you can write that as this, g of x times h of y. Okay? All right? In other words, your function f, which is a function of two variables, can be split as to be a product of one function that's x alone and the other function y alone. If you can do that, then the method, the way to go here, is to do separation of variables. Okay? If that can be written as a product form. Okay? This is said to be separable. You'll see this word. Or to have separable variables. Or separable variables. Okay? Either one of those. The function is separable or it has separable variables. And how you solve that is separation of variables. Okay? So here's an example. dy dx is equal to y squared times x times e to the 3x plus 4y. Okay? Does that look like it's separable? Why not? What part doesn't look separable? Or is it separable? Okay, that doesn't look separable, does it? Because this part is y alone, that part is x alone, but this has x's and y's. But think, though, aha, you're absolutely right. This can be written, then, as y squared x e to the 3x times e to the 4y, because if you have the same base, different exponents, keep the base, add the exponents, yes. Now you see that is indeed separable. Okay? You can separate, put these two together and those two together, you have functions of x and y. Now we're not about to solve that yet. We will by later in the term maybe, but not right now. How about this one? dy dx, good old first order ordinary differential equation, is equal to y plus sine x. Separable or not? Okay, I can see going through every trick in the book. Nope, not separable. Those pluses and minuses, which very good observation here, might think that might not be until you realize that's in exponents, and you can change the sum of exponents to the product of the bases. So yeah, that one was, this one's not. No way you can separate them, because they're not a product of each other. Okay? Now, that first one, like I said, you can rewrite that as y squared e to the 4y times x e to the 3x. Okay? That is separable. Okay? And you can write the, reverse the order of them, and put the x e to the 3x in front and the y squared e to the 4y in the back, then you have it g of x times h of y. Okay. Now, what they do from here, to me, just really confuses the issue. It's absolutely correct what they do, but it makes it so difficult to follow, okay? And I'll show you what I mean by that. What if you had a differential equation that looked like this? Some p of y times dy dx is equal to g of x. Okay? The question is that separable? What you think? Frankly, your only functions in there are already p of y and g of x. They are already separate. They go into, let's say p of y is some phi of y where phi of y over 1 over phi of, yeah, you can divide both sides by p of y, and then you have 1 g of x times 1 over p of y. Those are separable. Okay? So to me, what they did to this does not make it a bit clearer. In fact, it seems like it confuses the issue. Now, I didn't say how you go about solving this. I wanted to, but the book hadn't addressed it yet. Here's what I would do. Okay? Let me start with that very first one. Very generic equation here. Okay? And here's what we do. And I'm going to even take out this part here. Okay? There's our function. Okay? Here's what we do, folks. Write it in differential form. That would be dy is equal to g of x, h of y, dx. Right? Is that legal in most states? Okay? Then divide both sides by h of y. Okay? That gets rid of your h of y there. Now you've separated the variables. That's why we call it separable. You have one function over here, 1 over h of y dy is equal to g of x dx. And guess what we do then? Integrate both sides. Whatever this function is, if it's integrable, integrate it. If it's not, solve it however you can, numerical integration or whatever. Same thing here. Solve it. Usually we will still have only one constant of integration. If you want to have a C1 over here and a C2 over here, at the end combine them and they make the same some C. Okay? How about this really hairy looking one we have here? Okay? Down here, this one. Remember, this was not, so I'm going to do away with it. That's not separable, so you can't do it, so don't even try. Okay? This one. Okay? Same type deal. This is your dy dx, and write it in differential form, which would be dy is equal to y squared e to the 4y x e to the 3x dx. And guess what we do next? Divide both sides by y squared e to the 4y. Okay? And then we have 1 over, I'm going to write it differently, okay, if you don't mind. Okay? I'm going to write this as y to the minus 2 e to the minus 4y dy is equal to x e to the 3x dx. And guess what we'll do? Integrate both sides. Now, I'm not going to ask you to do it, but what would be your approach to a problem like that? Or like that? Maybe two different approaches. What would you try? This is good old Cal 2 question, isn't it? What would be your approach to this? I'm not going to swear that it works or not, but what would be a good first approach? It's an integration problem. So is that. Exactly. That's exactly what I would try on both sides. This be my, how do we used to call it? U and V. Let that be my U and this be my V. Is that right? It probably is going to get messy because of that. This one may not work that way. That one will work that way, for sure. You might have to do, I don't even know what you do with that, but you might have to do a substitution. Okay? But if you can't integrate it, do it by thing. But that's how we do it. Okay? All right. So, what about this one up here? And like I said, the book did all sorts of weird things to it and introduced new functions and all that kind of stuff. And I thought to myself, why? What would you do in one like that? This one right up here. What's the first thing we did here and here? Write it in differential form. And what would that be? P of y dy is equal to g of x dx. Why go through and introduce another function? Phi and phi prime and all this kind of stuff. Just do it this way, okay? This is just set up perfectly. Integrate both sides. And so, P of y, hopefully you can integrate that. If you can't, try some technique. If you can't, numerical. Whatever it takes. Do that to the P, do it to the G. They go through all sorts of stuff at the top. P of phi of x times phi prime of x and blah, 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 blah. And the thing is, it's just integrating P of x dy, P of y dy, integral of P of x, g of x dx. That's what you get, okay? And generally, you're going to wind up. Now, I know you're typically want to have a plus c here and a plus c there, but when you get to the end, move all the c's to one side or the other. Usually with the x, wherever you want to go. Okay? Now, enough of blah, blah, blahs here. They went through all this stuff and then say, and or you could just do it this way. So I said, just do it that way. So let's do example 1. Okay? Believe me, this is the best book I've taught from. I've tried several and they all stunk. This is the best one that I've run into so far. Man, how I wish I had the one I had in college when I was a third quarter sophomore. It was the greatest book. It almost help you teach yourself. You know, it's just so straightforward. Okay, here's this one. 1 plus x dy. They've already written it in differential form for you. Minus y dx is equal to 0. Whoa. This doesn't look like a differential equation at all. Well, it's in differential form. It is a differential equation. To get it via differential equation, we're used to seeing it, divide both sides, so to speak, by dx, and you have 1 plus x dy dx minus y is equal to 0. Yeah, oh yeah, that's a differential equation. Okay. So, what would you do to this? ultimately I would, but frankly what I like to do, and that is perfectly legal to do what you said, I like to separate the dx's and dy's. So in other words, I want to add the y dx to both sides. Okay? Is that okay? And that gives me 1 plus x dy is equal to y dx. Okay? Now, I would do what you said. You could have done it earlier, but I think now I like it better. What would that be? What would you do to get the x's together and the y's together? Divide by dx. Okay, gets you back to a differential equation. This is how I want it in differential form. So I want to divide by, okay, let's divide this up by 1 plus x, but then you have to divide this by 1 plus x. So that'll wipe out that, and you have dy is equal to y over 1 plus x dx. Now what? Not yet. I want the y on. So what I'm going to do? Yeah, that sounds good. Divide both sides by y. And that gives me 1 over y, like you said, dy is equal to, notice sound effects, 1 over 1 plus x dx. And now, integrate both sides. Now, they didn't give us any initial conditions, so we don't know much. So, how would you integrate the left-hand side? ln y equal to ln 1 plus x. And by the way, you probably should put your absolute values in there. And then what? Plus c. But you know what? Since everything else has an ln in it, and you don't have to do this, I'm just going to suggest to you, let's make that a ln of c. Isn't that a constant too? Okay. All right. Now, if I want to write that as a function of y, explicitly as a function of y, then I would do a little bit here. What do you get if you have the sum of two logs? What's that? What log principle? It's what? Say that again. Okay, what do you mean? Okay. I hear you talk about my hearing so bad I can't make out what you say.
Don't you do e to the ln to make it?
Okay, just a second. Just a second. I want to combine those two first. What's the sum of two logs? Yes, the log of the product. That's the log of c times 1 plus x. Right? Okay? And that's the log of y. Now you see why I put a log c out there? Made it a little bit easier to deal with. Now, take the e of both sides. E here, e there, and what does this give us? Y is equal to c 1 plus x. Okay? Now, I lost the absolute value signs. I probably shouldn't, but I think it's okay. Well, here's what they do. They do plus or minus c. That then will account for that. Because you can fiddle around with it to see. There's your solution. Okay? You have an initial condition, plug it in, see what you get. Okay? And I believe you would have to say y can't be negative. Well, but this says it can because you could have the negative c. But I guess that's only if that came out negative, then you would have to have the negative c. So you use whichever sign guarantees that the y stays constant. Because you couldn't do it otherwise. Okay? I think we just solved our first differential equation in the course, haven't we? Yes. I mean, all this has been, all this esoteric stuff up there, we finally did solve a differential equation. Okay? And actually, they left off that. They did the plus or minus at an earlier stage, but you really don't need it here because that will work as long as your x's and y's, if the x's make the right-hand side negative, then the left-hand side is going to be negative too. Yeah, so that'll work. There's your solution. First order linear differential equation. You have one parameter system. Okay, we found it. Okay, now let's move to I would like that a little bit better if your if they put it x plus 1, which really doesn't matter. And then you see that you have a slope of c and a y-intercept of c, y-intercept of c. And as long as you have that, you can draw your family of curves. Okay. So let's do example 2. I should have asked this before I erased it. Were there any questions about that? Okay. All right. This time they're giving you an initial value problem. Here we have dy dx is equal to minus x over y. Okay? With the initial condition that y is a 4, to me, is equal to negative 3. That's a condition. I don't like calling it an initial condition because to me initial would be y is of 0, but this is a condition. Y of 4 is equal to 3, which you can say, well, that's the only one we have that's initial. Okay. So what would you do to solve that? Anybody? Multiply both sides by y. That sounds like a winner. A winner. And multiply both sides by dx, which you're not supposed to say, but, write it in differential form. Okay? I'll still treat it as if that sound effect's included. What do you have here now? Y dy is equal to negative x dx. And what do you do now? Integrate both sides. Okay, and what does that give you? Y squared over 2 is equal to negative x squared over 2 plus, why not c over 2? Any reason not to? And that way I can just say y squared is equal to minus x squared plus some constant c. Okay. Now what is that? What's that describing geometrically? Yes, it's a whole bunch of circles, c being the radius, the square root of the radius, right? Or I could have done a c squared, and then it really would have been nice, wouldn't it? X squared plus y squared is equal to c. So, square root of c would be your radius. But since we know that y of 4 is equal to negative 3, we can plug it in. So what do we do there? Let's use our initial condition, our condition here. What does that give us? Anything? Help me. Okay. I heard a 25. Okay. How you got that was y was negative 3 here, and that squared would be 9 is equal to minus 16 plus c. So Sure enough, add 16 to both sides, and you get C is equal to 25. So there we have it. So go plug that back in. Y squared is equal to minus x squared plus 25. Or I want to write that as x squared plus y squared is equal to 25. And that would be what? What does that describe? A circle of radius 5, right? Circle of radius 5. Okay. Now, we have a problem, Houston. Okay. It's not really a circle of radius 5 because that's not a function, is it? So can we jump over to our graph paper? Now, what I just described to you was a circle of radius 5. And I don't draw circles very well at all, so I'll give it my best shot. There's a circle of radius 5. But we do know that y of 4 is equal to 3. So when x is equal to 4, y is equal to negative 3. Look at that. I even hit it on the nose there, didn't I? So what function do we have here? Not this part, but this part. It's the semicircle of radius 5 because we only used the portion of the graph which has our initial condition. So it's the semicircle of radius 5. The bottom half of the circle because of our initial condition. Does that make sense? Okay, good deal. Oh no! How could it be?